Hello, my name is Musa Mikhail. I will be presenting this paper on the security evaluation of AIS, the automated identification system used in seagoing vessels. This form a part of the assessment on the course Introduction to Cyber-Physical System Security at Georgia Tech. First, I will begin by acknowledging the contributions of the authors of the paper, Marco Balduzzi and Kyle Wilhot, both of the Trend Micro Research Group, and Alessandro Pasta, an independent researcher. This paper was first presented in the year 2014 at the annual Computer Security Applications Conference in New Orleans in the United States. The full content of the paper can be accessed in the link at the bottom of the slide. So a little bit of background. The AIS is the application of cyber-physical systems to smart transportation by sea. It is meant to enhance the safety of vessel traffic through, say, automatic exchange of up-to-date information, as well as tracking and monitoring of ships. The AIS worked by acquiring GPS coordinates and exchanging this via radio transmission between ships and also between ships and maritime authorities through what is called the vessel tracking services, or the VTS, that are located onshore. So some of the key benefits of AIS includes, but not limited to, maritime security through proactive vessel monitoring and mitigation against piracy attacks. The AIS has been found to be very useful in collision avoidance. It has also been used in the past for search and rescue operations. AIS has also been proven to be a valuable source of information to support incident investigations. Furthermore, authorities can actually use AIS for controlled communication of instructions to vessels, and can also be used for sharing weather forecast and other relevant information that can enhance safety of navigation. By 2002, AIS was made a mandatory requirement for all seagoing vessels with gross tonnage of 300 and above, and a mandatory requirement for all passenger carriers. And because of this, there is an estimated about 400,000 installation of AIS across the globe, and this is obviously growing due to the mandatory nature of it. So before we delve deep into the presentation, we'll take a look at how messages are communicated in the AIS. So as depicted in the slide, the AIS work by acquiring GPS coordinates and exchanging this and other relevant information regionally with nearby stations. So for example, in other ships or in vessel tracking systems or services, the VTS, through the VHF frequency. It uses two radio channels. One channel at 161.975 and the second channel at 162.025 megahertz to achieve that VHF communication. The AIS also use AIS providers online for relaying and rendering of VHF information. The providers collect data primarily from AIS gateways deployed geographically, for example, along coastlines, and in VTS operated by relevant authorities. However, other individuals like ship captains can also stream AIS data using mobile phones, or by composing specially formatted emails, or using specialized forwarding software to duplicate and send the AIS data as soon as it's been made available on board. So now we'll take a look at the motivation behind this paper. As we have seen earlier, the significance of the AIS and the safety of people and assets at sea cannot be overemphasized. And because of this, ensuring security of AIS is quite an important endeavor. Meanwhile, There are media reports showing that AIS information was in the past polluted with counterfeit information. An example of which is the report by Bloomberg of some Iranian ships that switched their flagged countries to Zanzibar in an attempt to wriggle out of sanctions imposed on them by the United States and the European Union. So this motivation is actually what guide the authors to conduct this research, which they claim to have been the one of its kind in the industry. And you can concur with the authors, considering the meager amount of literature available on the topic as at 2014. So the main aim they hope to achieve was to conduct a comprehensive security evaluation of AIS from both software and radio frequency angles. And to achieve this, they have to design and implement a novel AIS transponder using software-defined radio, and use it to demonstrate how AIS can be exploited by a typical attacker. In the course of doing that, they identify some of the key cyber threats and vulnerabilities that exist in the AIS implementation and its protocol specifications. At the end, they propose some practical countermeasures that can be implemented to mitigate the threats of an attacker. However, because of the ethical concerns that tampering with the AIS information may raise, the authors tried to limit their experiments to harmless AIS messages that doesn't interfere with existing services. Also, in their own radio frequency exploits, they they try to simulate their own experiments using a physically connected equipment to avoid transmitting radio frequency signals that could be picked by other AIS transceivers. They also ensure that they conduct all their experiments on land, far away from water bodies. And finally, they ensured that they have contacted all the software providers and even standard organizations like International Maritime Organization to secure consents before progressing with the experiments. So, like I've mentioned, the researchers or the authors have actually looked at AIS both from the software point of view and also from the radio frequency angle. So during the software evaluation of the AIS, the researchers made reference to the AIVDM, which is the application layer protocol used by the AIS to exchange messages from, say, a vessel transponder. Uh, for example, a vessel transponder might be transmitting the vessel's position, or from VTS to monitor ships that are already at port. The IVDM actually specified 27 different messages, each one having a corresponding purpose and a value that designates its purpose. So for the purpose of this research, the authors have actually implemented a tool they call the AIVDM encoder in Python, which they use to generate arbitrary AIVDM sentences like the one shown on the slide. They use the AIVDM encoder to conduct both the software and hardware um, evaluations of the AIS. So for example, the AIVDM message that we are seeing on the slide indicated a vessel used for military operations located somewhere in the coast of Italy. In subsequent slides, we will also see how the authors were able to encode valid AIVDM messages describing fictitious vessels that doesn't even exist at all. For the radio frequency evaluation, the authors have to design and implement a system for the transmission of arbitrary AIS messages over the air. They call the system the AIS-TX, which they do implement on top of the GNU radio framework. So as shown on the slide, the AIS frames are generated using the AIS frame builder, which implement the full stack of the AIS framework. The Gaussian minimum shift keying modulated signal is then generated using the internal modulators in GNU radio, which are then transposed to the default operating frequency in line with the AIS specifications. The modulated frequencies generated then at baseband are then transposed to the default operating frequencies in line with the AIS specifications. To prevent signal clipping and distortion at the analog digital converter, we can see that the researchers have to reduce the amplitude of the signal from 1 to zero point 0.1 through attenuation. Finally, the signal has to be shifted over the carrier frequency of 162 megahertz to generate two signals over the AIS frequency bandwidth specification. Like I've mentioned earlier, the 161.975 to 162.025 megahertz. So this is actually the layout of the transmitter used by the authors in carrying out their research and experiments. So in the paper, the authors were able to identify three different category of threats. They further categorized these threats into three different classes for the purpose of the evaluation based on the channel through which these threats can be implemented. So the first category is called spoofing, where the attacker will create a non-existing asset or condition, and we will take a further review on the various types of spoofing the authors were able to identify in the course of their research. And the second category is hijacking, where an attacker will change the AI VDM message content of an existing AIS installation. While finally, the third category, which is the last category, is availability disruption threats, which are basically classical denial of service threats that an attacker can implement against a target. So as I've already mentioned, some of these threats can be executed through a software provider, either through the mobile applications they provide or the existing avoidance softwares used by individuals. Some other threats like availability disruption, on the other hand, are often implemented in the radio frequency space without having to change the message being streamed to the online platform. So most of these threats can also obviously span across the two domains, both software and radio frequency spaces, and are categorized as hybrid threats. So we'll take a look at some of the threats and some of the experiments that the authors were able to implement. So it's spoofing. So spoofing, as mentioned earlier, involved creating a non-existing asset or condition. So for example, the authors identified 5 different ways through which spoofing attack can be implemented on the AIS. So the first type is what they call ship spoofing. So in ship spoofing, the attacker craft a valid non-existing ship, and the attacker might even decide to assign a fictitious static information to this non-existent ship, say for example name, call sign, flag country, cargo type, manufacturer, and even dimension. The attacker also have the leverage to give the crafted ship dynamic information like ship status, say if it is underway or at port. So for example, destination, speed, and even position in course. So the authors also mentioned that an attacker might also spoof a search and rescue aircraft because these aircraft are also expected as per regulation to have AIS transponders installed on them. So as we can all imagine, this type of attack provides a wide surface of malicious scenarios. For example, spoofing a vessel into a jurisdiction of an adversarial nation. The second type of spoofing attack identified by the authors is what they call the ATON spoofing. ATON is actually an acronym for Air-to Navigation Systems that are used to assist vessel traffic to avoid hazards and adverse conditions like piracy attack and bad weather. So in this type of attack, a fake information is crafted to lure a targeted ship into conducting or self-maneuver. So for example, a fake buoy can be spoofed to guide a ship to navigate into lower waters and get it grounded. The attacker can also trigger a collision attack on a targeted ship by spoofing a fake ship on the collision course of the target. Also, this might cause panic and unsafe maneuvers that might result also on incidents. So another type of spoofing attack also identified is what the authors call AIS SART attack, where a fake distress signal of a man overboard at coordinates chosen by the attacker is spoofed. And since all vessels are required as per regulation to join in search and rescue operations, this might lead to vessels to be lured into a hostile sea space. Finally, An attacker might use AIS to send false weather forecast that could endanger the safety of other vessels by, say, for example, communicating sunny weather when a squall is being expected. So these are some of the spoofing attacks that the authors were able to identify in the course of the research. I will take a look at some of the experiments the authors were able to conduct to really demonstrate some of these attack scenarios. So one of the experiments conducted by the authors involved the use of the AI VDM encoder to craft an AIS message indicating a low tide at a nearby lake. So if we look at the AI VDM message at the top left corner of the slide, um, we can easily see that a message type 21 is indicated, showing that the message is actually received from an assist to navigation device, and type 33 actually designate a buoy. So it's actually indicating that there is a buoy reporting a low tide at a particular location. The authors were able to use this information, communicate it to the online providers using a generic networking client over the internet, like Netcat, and get them to render this information without any hindrance. They were also able to successfully craft a formatted email report of a moored vessel and send it to the email address of the targeted subway provider. And this same email was used to also render the vessel, the ship that the email was actually referring to without any inquiry from the providers. Finally, the authors were able to implement an automated script that used Google Earth KMZ files to make a spoofed AI station to follow a predefined path over time. So in the slide, we can see the result of the experiment where a fictitious ship was made to follow a path that spelled pond in the Mediterranean Sea. And all of these attacks were executed without any hindrance from the providers. Now, in their own radio evaluation of the spoofing attack methodology, the authors were able to conduct another experiment on collision spoofing. So to implement this attack, they spoofed a vessel colliding with a transponder they have implemented, as earlier mentioned. And then they used the coordinates and the course of the targeted ship's transponder to fake a ship navigating within the closest point of approach threshold configured on the target's transponder. So the image at the top right shows the AVDM message sent by the spoof ship containing its location, course, and speed. And the picture in the middle of the slide shows the signal lights being triggered because the collision is expected to happen. And of course, based on the report shown, the alert trigger that the collision is expected to happen in the next 3 minutes. So in this kind of scenario, a targeted ship might, in an attempt to avoid the collision, change its course into a course that is actually what the attacker is desiring to achieve. Now, looking at AIS hijacking, as I've mentioned, AIS hijacking involves changing any information about an existing AIS installation. So it doesn't involve the fictitious creation of fictitious assets or conditions. So, for example, information about the cargo, speed, location, or flag country of a ship can actually be changed to a different information. So the attacker might also maliciously modify the information provided by AT devices provided by the authorities. So this kind of attack is not only limited to ships alone. It can also attack VTSs provided by authorities. This kind of attack was also, as mentioned by the authors, can be executed in software or in the radio frequency domain. So in the software variant of this category of attack, the attacker will have to first eavesdrop on the communication from an existing AIS installation, then replace the AIS information, mostly the AVDM component of the message, with an arbitrary information of his choosing. In the radio frequency variant, on the other hand, the attacker override the original message, say by sending a higher powered fake signal over the same frequency, therefore attenuating the frequencies, the this original message and replacing it with its own. So in both variants, the victim will end up receiving an attacker modified version of the original sender's information. Look at some of the experiments, hijacking experiments that were conducted by the authors. So in one of the experiments conducted, the authors employed a man-in-the-middle attack methodology to demonstrate how the message sent by a target can be intercepted and modified by injecting an erroneous data. So for first, the AIS message is physically intercepted through an AIS gateway deployed by the authors. They then use a proxy server to intercept, modify, and then upstream the modified information to the online provider's portal. Um, the authors reported that the online provider accepted the tempered message without any hindrance. And as we can see on the example shown on the slide, the location of an existing ship was changed from New Orleans to a lake somewhere in the Dallas area. So this kind of a report, this kind of attacks can easily be implemented without any of the online providers being aware that the information that has been uploaded on their portal has been changed. Now, looking at the third category of threats, the availability disruption attacks. As I've mentioned earlier, availability disruption attacks are a variant of the classical denial of service attack. So three different types of availability disruption attacks were identified by the authors in their work. So the first one is slot starvation. So in slot starvation attack, um, the attacker would be impersonating the maritime authority to reserve the entire AIS transmission address. So while doing that, it means that the attacker is preventing all stations within the coverage area from communicating at all. So this type of attack can affect obviously both ships and ATON systems as well as even AIS gateways used in monitoring vessel traffic. It is obvious that this kind of AIS attack can actually interrupt or disrupt AIS communication on a large scale. The second attack methodology called the frequency hopping attack, and in this kind of attack, the attacker will impersonate the maritime authority also to instruct one or more transponders to change their operating frequencies. So by changing their operating frequencies, the attacker is now rendering those AIS installations useless. The third type of availability disruption attack identified by the authors is what they call the timing attack. Here, the attacker instructs the targeted AIS transponder to either delay its transmission rates or increase it to a very, very high rate. So by simply relaying the command several times, the attacker may, for example, render the targeted responders inoperative. And so this type of attack can make a vessel to completely even disappear from AIS-enabled radars because it cannot transmit or receive AIS messages. So we'll take a look at some of the ADT experiments that were carried out by the author. So in their implementation of the frequency hopping attack, the authors verified that by broadcasting the message shown on the slide, they were able to immediately switch their own receiver to non-standard channels, therefore making the AIS receiver unable to receive, say for example, the position of nearby ships. So they were also able to demonstrate that by conducting a frequency hopping attack, the transceiver might also be prevented from transmitting, so broadcasting its own information to other vessels. So this completely blind the transceiver. So taking a closer look at the AI VDM message on the slide, we can see that this operation applies immediately because a geographical location with the current location are both specified explicitly. But however, an attacker can actually program the device to also disappear from AIS monitoring upon entering a particular, say, sea area or sea space of its interest. So, for example, a pirate ship might be made invisible upon entering the sea area around Somalia. So, this is actually a very, very potent and a dangerous attack methodology. The authors were also able to implement a timing attack, which is basically similar to the frequency hopping attack. However, here the attacker attempt to inhibit the transmission capabilities of one or more AIS stations by changing their rates of transmission. So by repeating this command, say for example, asking all the AIS transmitters uh, to delay their transmission by 15 minutes and then repeating this command using an iterative software routine, the attacker can execute full denial of service attack on his identified victims. The attacker might also overload the maritime traffic by requesting the existing stations within a region of interest to be sending AIS updates at a very high rate. So therefore, the author had the option of either slowing down the rate of AIS updates or increasing it to unmanageable rates that can actually hinder the system's ability to transmit and communicate effectively. Now, after all the evaluations that were carried out by the authors then go ahead to propose some countermeasures that will be able to help mitigate against the identified threats. So two key mitigations were actually proposed by the authors. So first is anomaly detection. So this strategy involves the application of anomaly detection techniques on the AI's collected data to detect suspicious activities like, say, for example, unexpected and sudden changes in ship's course, or it's even static information. Say, for example, an unexpected changes in the dimension of a ship. In addition, the AI's data can be correlated with satellite and radar information to find inconsistencies. This can also be applied to both static and dynamic information about the vessel. So although anomaly detection can be a valuable means of collecting and analyzing information, it is still not very effective for the AIS transponder that are installed on board the ships because these transponders are also vulnerable to radio frequency attacks. So for these reasons, the authors made a recommendation to complement the anomaly detection measures with a public key infrastructure schema, which is to be embedded into the AIS protocol used for radio frequency communications. So they suggested the use of the X.509 PKI uh, digital certification process, where digital certificates issued by an official national maritime authority, in this case acting as a certificate authority, can be configured in a transponder concurrently with other station identifiers like the MMSI and the ship's call sign. So they also propose that there should be two ways should be used to manage the issued keys. So first, they propose that certificates belonging to verified stations like VTSs are preloaded via onshore installations. So for example, when a ship enters ports, the um, the certificates that are relevant to that port will be preloaded at the port. On the other hand, generic certificates and other certificates previously unknown to a station are exchanged with nearby stations on need-to-do basis. And of course, vessels that are equipped with satellite internet access uh, can actually retrieve relevant certificates through online certification services. So these are the two key countermeasures that the authors were able to propose, which they believe could help in improving the safety the security, sorry, of AIS installations across the globe. So in conclusion, the authors were able to demonstrate that AIS is a very useful technology used in smart and safe transportation of people and goods at sea. They also show that AIS is a very popular technology and is growing from strength to strength. As of 2014, there are more than 400,000 installations of AIS across the globe. They were able to carry out a comprehensive security evaluation of AIS and demonstrate some of the key threats and vulnerabilities that are inherent to AIS. They are also able to demonstrate that these threats can actually be implemented from both the software angle and also through the radio frequency communication protocol of the AIS. Furthermore, the authors were able to also demonstrate that they reviewed some work in the literature around AIS during the course of their research. Um, a key of the ones that they were able to highlight in their paper was the work of Zambiao et al., who use online analytical processing tools to store, process, and correlate information for collision avoidance and uh, supporting incident investigations. They have also highlighted the work of Cathell et al., who actually conducted some research on multi-sensor networks for data surveillance. They suggested the extension of the algorithm that was actually used for undersea surveillance network to improve the effectiveness of the AIS. However, the authors of this paper claim to be the first to conduct a security evaluation of the automatic identification system. And considering the meager amount of literature as of the time, that is 2014, I can actually concur with the claims of the authors. So thank you very much for listening to my presentation, and I look forward to receiving your questions in due course. Thank you very much.